Hello, good evening. Today's topic is going to be about hardware and data synchronization. The trigger for this talk comes from Googling on the web about I2C, a communication protocol used on hardware level, and giving my kind of philosophical point of view how to interpret this, or at the very least how to explain this to people who don't really know anything about IT, or even more specifically about the hardware, or even more specifically digital systems. So let's dive in. Without any further ado, just imagine that you have a timeline between these two hands. Here you have clock in between that's going to be ticking. Tick, 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 tick. Each of these ticks is going to now signal to us when to reinterpret our actual signal. So we have got one signal here, which is tick, 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 tick. Something we could regard as a sampling rate, kind of. And the second is the data, which would be, at least in my case right now, with the chin being the 0, with the top of the head being the 1, or let's say skin and the clothing. And if the skin is 0, we have dum 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 dum, and when we have 1, dum dum dum. You can add voice here, you can add sound here. The point is, whenever we have a new clock hitting, we're going to recheck, so to speak, our data, which means that if our clock is very slow, let's say that our timeline is here and the clock is within that range, only like one tick, one period, then what we get is just only one signal. Is it 0 or is it 1? Is it 0 or 1? But if we can compress it, now that's my imagination here, the signal such that the frame of reference, that's the timeline, is still here, but the clock itself is now getting smaller and smaller and smaller, at least for the frame of reference, and what we get is now tick, 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 at least 3-4 times already, which means that every time we're going to interpret, we'll have new value on the other line. 0, 0, 0, 1, 1. Get it? And the more you can compress it, the denser it gets to the reading part. Tick, 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 tick. Or should I do it like this? 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 0. A little bit too fast, but I can't ever imitate what it's going to take place in the computer, where we have already 1 plus gigahertz of frequency. That's like 1 billion times per second. I can't mimic that, but the essence is still the same. It's very small period on timeline for the clock cycle when we're going to reread or reinterpret the next bit in our data stream. And now when it comes to clock, or clocks in general, why this matters, it's because when you have clocks with different frequencies, or when you have different devices separated from one another with different wire lengths, how do you synchronize data from one going to another? How do you synchronize the compression rates, so to speak, in respect to frame of reference, which by the way could be used as a so-called absolute reference, but it's abstract, so it doesn't actually exist. What does exist though is our crystal, which is generating these hits. And if we have lots of those devices, each one of them with those respective crystals, each of them being in hardware, each of them being subjected to the real world, whatever circumstances, conditions, from physics mostly, by temperature, by humidity, by expansion, by contraction. You might think it's like it's all sealed and isolated, right? Well, by engineering, Yes, that's the ideal, but we always have some errors inside. Errors by the design, by the manufacturing, and errors by the environment. So, or at least there's a chance for this. So you can't really reliably go like 100% we always have the synchronization. In data, you could overcome this by counting some cycles and checking, doing so-called comparisons between the data streams if you know you're going to you need to have copies, for example. But for everything that you want to check for reliability in hardware, you require either greater surface area, more wires, more time, and of course more power, or let's say more energy. Or another way of saying it, you will have greater overhead per original data that you want to get across the line. That is why it's so important to address synchronization as the utmost importance. Now it goes a little bit out of the topic right now, but if we are imagining our brains, or let's be even more specific, brain-computer interfaces, inside our brains, embedded to our brains, or at the very least, if not inside, then ability or able to read our brain waves and interpret those as thoughts, then synchronization will become an issue. Not synchronization as to when the neuron fired necessarily, but even though that would be like physiologically very important, but on the so-called perception level, when we think we had a thought. In my noting system, I use internal references for that purpose, but it's not always going to be accurate enough because, well, I'm a human being, I'm limited by how fast my fingers can type, and I'm also limited by the concurrency within the topic, or of the topic, because new thoughts might emerge as I'm trying to summarize. Something that has very, very often happened to me when I'm recording myself outdoors. The same happens here. But back to the main topic. If we have a timeline with a clock, then if we compressed the clock period in respect to our frame of reference, we would increase its frequency, which is going to indicate to when we need to reinterpret for the next bit or the next singular, the most, like the smallest unit of perceivable data in the data line. If our clock was like this, it would be like, we said it's always the same. If it was compressed, we say, okay, my pitching is not very good for this explanation, so to speak, audio type explanation, but you get the point. You have zeros, you have ones. The advantage of this approach, although it's very discrete, is that it's very, very simple. Now I have to admit that it's right now on an abstract level, it's a theory. In reality, however, that's not exactly how you would necessarily get the output of your system. You don't always get the output, or at least you wouldn't get the new valuable or required output every clock cycle. Because clock cycle would be kind of like pushing the signal until the next gate, until the next stop. Get it? So if you had a digital system with all the AND and NAND and OR, XOR, NOT, you name it, gates, like on a gate level at least, then with each cycle, the signal changes, yes, from the input, I give you that. Like, let's say we change the input, we have a new clock, we have now a new kind of, I won't say function necessarily because functionality is dependent on the gates, but let's say we have now a new input vector, and it's going to be, at least on the hardware level, passed through the entire schematics step by step. That's why for some operations, let's say in assembly when you want to do something, you have multiple clock cycles. Some operations might take like 3, some might take 4, it depends. Of course, with RISC or like reduced instruction set architecture computers, we would like this to be, how to say, reduced number of clock cycles per operations, because the operations themselves are already so simple. They're not like CISC complex instruction set architecture computers where I can't say every imaginable, but a lot of math operations could be embedded into a specific hardware to begin with. Whereas in a RISC architecture, you can just repeatedly do the same thing over the scheme, and you still get the same result. It's about redundancy, and it's about coherence. And now coming back to the clock issue, even though it is doesn't really dependent on the architecture you choose, like the clock is kind of like a separate part. It's the way you would compress the sampling rate along timeline. I would say, now that's my proposition, or at least my kind of ideation here, the more you go with repetitive tasks, the more you have to rely on long-term reliability, because you will have more of the same type operations done in the process. However, though, if you say that it's complex, that is, we require a very small number of operations to get the same result, but the hardware itself would be very, very complex. Or how to say, if you had an error in the system that is you detected, here in RISC architecture, when we do things repetitively, you can jump back to the original part quite soon, because you can do the checks after every iteration, right? Which is an advantage. It's as if we allow injection points, so-called temporary observation interruptions, to see whether our data is correct or not. Like, is this sequence from the beginning of when we initialize it until we really get the answer, do we have anything that is either lost in the process, that's getting noise emphasized or noise amplified in the process? We can detect it much faster. But of course, as always, with every observation, you either have to like plug it in the middle and kind of check it. Now, nowadays, what Caltech ICT, Computer Systems and Reliability department is doing is focusing more on software-based self-testing, which means that you don't even have to plug anything in between to check every line on every 2 gate connection, or if you go on higher level, every register to register connection, or even higher level, every component to component connection. But instead, you're going to run through a test vector, like a set of test vectors. By test vector, I mean that vector as having one dimension, right? Matrix would be like 2 dimensions, tensor would have 3, but vector is 1-dimensional. So we have input here, let's say 32-bit architecture, so 32 different either zeros or ones, and we have different sets, like a set of those different combinations of inputs and outputs, kind of like a film we're passing through. And each of them is going to test certain nodes in the system. And by node here, I mean not from graph theory necessarily, even though you can apply this here as well, but you have either on transistor level view, is the transistor functional or broken? Is there a short circuit? Is there an open circuit so that it's like kind of broken? Short circuit means that it is connected to another line where it shouldn't be, so they will have the same signals. If you have a current on one part, it will already automatically affect the other part, as if the other part, which had its own respective argument, would have no, how to say, it would have no saying for the system, right? So if this is already one, because of the short circuit here, this line here which actually should be only dependent on this input here, would always be 1. That's just one example. It also could be dependent on, as in real world scenarios, temperature, so contraction, expansion, and which would affect the current flow, and which might reduce the threshold from which we say it's activated or not, like when it kind of clicks the transistors or click transistor, and we get the wrong value because of this. Although that would be like very extreme temperatures, for which of course as engineers would already do it. They isolate it from the environment much enough so that you don't have this problem. But still, as for the synchronization, being it on transistor level or gate level or register level or component level, you will always have a chance for errors. And about the film part, when you're moving through it, you have those nodes, whatever these represent. What you have on the output, as by theory what we should have, compared to what we actually have, if they match, then we can say that with just software level approach that we just put in this test vector, knowing the architecture inside, or let's say the internal connections and their, can I say, converted interpretation, even though it's very philosophical here, but if you have AND gate, then how do you interpret on the, what is the interpretation on the output? On the input, it's this has to be true, this has to be true, at least by Boolean algebra. So this on the output here will be true only, or at least it will give current to the other side, if these two here are also true. Get it? And that's why it matters. That's why it matters to first synchronize, so that when we read signal from the first path, it has to be synchronized with the signal from the other path. If there would be a lag in between, even within the same chip, then even though it was 1 here with this input, because of the clocking, we don't really get the output from the AND, because for some reason the second dependency, the second argument, either was lost or didn't get to the AND gate in the right time. That is what I'm trying to make, or making point here. With every clock cycle, you don't necessarily change your input vector. That's very important here. It's as if you are forcing some of the input vectors to wait, so that on some level and deeper, let's say the 4th or 5th level of the nodes in the system, the signals from inputs haven't reached a place where you could have the following computation. However, though, you can be smarter here and don't have to wait everything all the time, because that would be like the worst case scenario, that let's say the first input would be connected to the last output gate, whereas the second input would have like 10 gates in between, which means that you would have to wait for at least 10 cycles until this gets propagated to the last part, and then you continue, like then you can forget the first input, right? It's a little bit problematic here, because the first input would have to wait too long. Now you could say, what if you could use memory for this, right? Like the first, it goes too much maybe into details, but like in my thinking, but what if your input vectors would be dynamic? That's a little bit complex here. It's as if you are having a parallelism already on the input level. So the inputs are not just like input vectors as 1, second, third, fourth, but more like 1, and some part of them can be forgotten almost immediately, and now you will have like that's a very tricky part here. You would have 2 sets, or maybe even 3 sets of interpretations of those inputs. So let's say you have 32, let's make it even simpler. You have 8-bit architecture system, right? But you're not giving new input every second, like like every following clock cycle. Get it? Which means that, let's say, the first two values in the vector can be already forgotten because the second operation is actually only dependent on those two vectors. But we can only do this if there are no dependencies of these in the real time for the first operation. Get it? So the first operation assumes that you have to go through, let's say, 4 levels of depth within the digital circuit. Then if the first two arguments here have already done their job, that is, let's say that they will be the one that are going through each of those nodes, that is, even if we deleted those now, the propagation would still be in the system because of the clock cycles. That is, we signaled this passed first, this has a reaction. On the second clock cycle, this is going to be reacted to this one, right? On the third clock cycle, this gives reaction to this one, and so on, right? But as this is happening, we can already have these inputs changed so that, at least these two, so that we can already start the second iteration. However, though, if there are 8 bits, what about those bits which don't go through 4 of those? Maybe they're only like to go through 2. They have to wait until these two are passed through for the 2 first arguments, so that now they would have a combination where you have the 2 first propagated through already these 2, and then the last 2 ones coming directly to the 3rd layer and then to the 4th. That is, these 2 can already change as if we now have temporary 2-bit architecture. It's a little bit different. I don't want to call it architecture here, but we have like 2 bits which are like capped, and then we have those 6 bits which are still needed for the first operation to be finished. That is, the first operation needs these only temporarily to be active or true simultaneously with all the other 6 bits. Which means that these 2 now can be altered, given that because they are hardware connected. That's not the problematic part, because they are already connected to the hardware itself. So if these 2 fire now, let's say on the second clock cycle, they change their values, only these 2, although how do you change these? Like, there will be some kind of control mechanism for that already. It's as if in the marble machine by Wintergatan, that those balls are falling, right? And now imagine that you had a vector of these, but each ball would be like, each line would be separated from one another. Input vector as all on the starting line, but only some of them going one by one into the system, right? The same happening here. So even though we have 8-bit architecture, for some operations which can be done with only 2 bits, let's say the 2 first ones, we already do the operation that can be done with the connections that they have with the nodes that correspond to certain functionality that will only have dependency on these 2 vectors already on the second cycle. Get it? So even though we have 8 bits, we can divide them by clock cycles based on the hardware encoded functionality. So even though we say it's 8-bit architecture, sorry for reading that word too much, we can calculate and compute and interpret our signals in a fractured mode for the entire data space. That would be an idea, how to solve this on hardware level, or how to even address this as a potential increase in the efficiency, how you connect human brain to a computer. That's a challenge, because what you have here is synchronization as a frame of reference by the clock versus synchronization of the inputs that is dependent, or that are dependent on the entire hardware embedded architecture. Get it? That's what it means to be an operating system on a hardware level. But this is still only, at least in our case, binary, just zeros and ones. If you had, what if you applied quantum computing to this? You can use the simultaneity, right? You're not computing faster per line, but you can do things in parallel. But the problem with quantum computers is that they require very, very, very high degree of isolation because of the near zero temperature requirement, like near zero Kelvin degrees. So you can't, or at least right now, well, in future, yeah, we will have this exponential growth and all that, but we can't really have this on the phone right now or in our PC. But do we even need that? Because if the PC is only required to send a request of what you should be done, and the processing happens somewhere where the temperature requirement is fulfilled in some kind of, I don't know, northern Sweden, for example. It doesn't have to be actually Sweden, because we don't have place on Earth that is so cold, right? Right? And I mean, some kind of conspiracy theorists might be like, what if, right? You know, something inside Earth. Forget that. The point is, the cooling and the isolation for the part that actually processes the whole stuff, which can then of course process simultaneously from different users, but it has to be tagged somehow in order to know who sent the request and whom to send it back to. Like it's like the data itself would have memory. Get it? So that unique identification per requester would be embedded in the data itself. But that's a little bit different topic already, as if I was sticking on the topic, but still, if we don't take the quantum part and we just still remain with the either ones or zeros, actually quantum is still 1 and 0, it's just that it's parallel. It's let it be for now. If we have not discrete system as zeros and ones, but instead we have continuous analog system as with our brains. That is, you don't need to have like thresholds from which you say that if current is kind of here, then we interpret this as 0, or if it is here, we interpret this as 1. Oh, and by the way, small remark, I say 0 is down here and 1 is up here, right? It doesn't have to be like that. It could be like negative logic as well, where the signal that is with higher voltage or current value, depending on how it is read or what is the criteria, what is the so-called parameter for triggering, or what is the parameter by which the thresholds correspond to the triggering. Yeah, very complex wording, right? So that we could have the 1 down here and the 0 up here. But that's just how it is interpreted, like this higher voltage or higher current corresponding to 1 and 0, but that's a little bit different topic. Just reminding you that 0 is not always down here, because it's us human beings interpreting the functionality. It's not like having like 0 point here and then we have like always increasing going upwards, how it's usually done, right? It's as if, even though it doesn't really make sense that way to interpret it, but we take the frame of reference with the arrow pointing that way somewhere in the infinity, and then just flipping it and having the arrow pointing here, as if we were going on the plane infinity, 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 and suddenly 0, right? Doesn't make sense. And like, where is the 0 in that case? Somewhere up there? What? Anyways, back to the analog part. If we have analog computers, in the past at least we had, very slow, very unreliable, and yet now we want to have analog because it is mimicking our actual brains much closer. But the problem with this in combination with my idea or ideation for dividing this 8-bit architecture into smaller bits so that we could have like micro bit dependency operations, yeah, very fancy word, done almost sequentially by the sampling rate for the clock cycle rather than by the number of cycles per initial or previous operation. Get it? So we combine these and integrate this into the brain or with brain signals such that it would be more continuous now. And each of those nodes in the architecture would have its own activation function. It's not anything new. It's just that my question here is, if we have those temporary micro operations within the architecture, let's say within the input vector for or by the architecture, then if we have continuous functions as in neurons and we have a dependency on their previous firing and previous wiring, then we're going to overwrite there might be an issue that we might reactivate a signal which you don't really want to be activated in the first place. It's as if, because of the rewiring, some of the connections get so strong, let's say, the signal will go through that connection faster than from the previous ones. So we can't just say that the clock cycle like tick, 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 but the clock will act differently, or at least the speed from which it reaches the other node is different. And this is problematic because it is fundamentally going to turn the entire system into an asynchronous system. How do you control that one? You could say, well, if there was a checker somewhere on the background, some combinations of the output which don't make any sense, you just drop away, right? But when do you do that? Like, what is the reference point in that case? Maybe that's the way we could define consciousness. Why? Because, I know, philosophy here, but yeah, hello. But if this happens, I'm just wondering here, what if we can define consciousness as not something abstract, but how we have dependency on altering the input vectors, and within that input vector range that we get through or pass through at any time, we have those micro input vector sets, or the fragmented inputs, which can be run or interpreted separately, even within the same architecture from the same through the same nodes that are still used by these ones, like these remaining input vector values. I said that the word use, right? Who uses who? Data using the architecture or architecture using the data? Well, philosophical question. The point is, consciousness, just hypothesis or like wondering, could be derived based on the asynchronization of analog signals on the lines which are dependent on the previous signals and thus increase or decrease their intensity and thus the power to activate any other node on the line. It's as if we had a clock. No. It can't be like that. The entire purpose of having a computer is that you can define your clock and you can manufacture it, and you can, it's a kind of like a confirmation that it's all going to be working magically together, right? But in human brain, do we even have a clock? And even if we had let's say in the brain-computer interface, how would we interpret it? How would we convert from one to another? That's the question. Assuming that we always can't get access to every neuron, we don't have information about every single connection, at least right now in 2018 October, we don't have, unless you had your brain cut into pieces and you kind of printed and then had this 3D model, but that would be a little bit, you know, too expensive, too long run, and of course it would be, you know, because you got the brain, you will be killing a person, so it doesn't really come up as a solution, but we need to have something which would work on normal human beings, like for me, for example, and put this into action. So, I mean, like massively, like long run, globally, just like, you know, futuristic vision. What's the applications? Why do this? So that I could have these talks as voice in my head already done outside without the need to record on the camera. Or even more, I don't even have to talk as for the camera right now, but I could just have it thinking in my head. And if anybody has interests based on the keywords that I have in my head, that's voice in the head, which are now tags, they can kind of jump into my brain podcast or braincast and listen to my voice in my head as if it was theirs. Anyways, that's the future part. That's where I'm going to go flipping away a little bit, like, but back to the little bit more technical part aside. Timeline, frame of reference, compressing the sampling rate as a way of just showing that we are increasing the frequency, and this indicating to how or when, not actually how, but when we will interpret our input signal. Is it 0, 0, 0 or 1, 1, 1? And for each of these interpretations, on the data line, we have, after some kind of bulks of those inputs, oh, we have another problem here. Sorry for the interruption here, but because if we have a wire, right? And the wire is sending these signals as lower current or voltage or higher current or voltage. But that's only, but it's still analog, right? It will be sequential. So if I have, let's say, 1, 0, 0, 0 on here, then on the output here I would have like 0, 0, 0, 1, and I have to flip it. In which case I would have to wait for each of the inputs to kind of go into the line to form the input vector in the first place. Then go to the operation, but if the input here is 1, 2, 3, 4, 5, each of them with their own clock cycle. Is it even dependent on the clock cycle? Or should I say, should it be? I have to think about this a little bit more. Anyways, in summary, number 1, having frame of reference and compressing our clock cycles on the timeline to have higher frequency and thus more like denser interpretation of the data on the other line. And number 2, proposing micro bit fragment architecture such that the input vector with 8 or 16 or 32 or 64 bits could be already altered by its inputs, so that we could have 2, 3 more, whatever you name it, different operations to be interpreted on the output in the same architecture simultaneously. Meaning we don't have to wait for the first operation to finish until we get to the second combination of inputs on the other side. So it's not going to be like inputs passing through output. Now change the input vector and start over again. What I propose is that even though we require some of them to be already the entire process time activated, some of them, let's say 2 or 3 bits, with their already existing connections with the hardware to the hardware, can do their own operations in a parallel. You could even say that would be maybe not necessarily the same, let's say the part here which is responsible for the function from 1 to 10, but you have functions 11 and 12 here, which if they occur can already be done with the first 2 inputs only, and it's going to be enough. We can flip them. It's as if like the first function going through this set of nodes, set of gates, set of registers, set of components will be ready by one time, but simultaneously as this is being processed, we can already fully execute the first one. That's now a little bit problematic here. Like, this is fully going to be executed. So like, first operation is like this time, and then at the center here somewhere we have a parallel operation that can be done as an intermediate one without interrupting the overall process. Of course, if you had like functional dependencies on the output, that this has to be first and this is second, then they will have to keep the second operation in the memory somewhere, because it was like done here, it's already completed, so we have to like retain it to make it comparable afterwards with the first function output. And why the second function comes faster, because it's only dependent on these 2 bits which do not really play any role for the first operation. But the problem now is that if you have more functions in the chain, like third or fourth or fifth, then the input vector has to be like, it's gonna be complex, like how to optimize this one. Number 3, connecting all this, however discrete and binary, with actual human brains, as in BCI or brain-computer interface, and wondering how we can convert all our analog signals between the neurons such that we have a dependency, or at least because we have dependency on the thresholds which are dependent on the so-called intensity as to how fast one neuron can fire to another. That is, the synchronization by some kind of static sampling rate wouldn't work, because the neurons themselves would be communicating faster to one another that have been rewired in the past. And number 4, proposing, or at least ideating or having this kind of statement that, at least by philosophy, you can define consciousness, but because it's dependent on so many continuous interconnected variables, you can never have a formal representation of it, because you will always have a feedback within the system itself that would alter its initial values. It's as if the dependency was always dynamic. You don't have a finite set of requirements, or like a little bit too high level actually. You don't have a finite set of conditions. You might have per neuron, okay, I give you that, but for the entire interconnected system of neurons, not like 10 of them or hundreds of them, it's like billions of them, then the consciousness would be an emergent property of n greater than, like large greater than 1 billion, let's say 1 million actually here, set of nodes which are any direction connected. So it's like multi-directive, it's like full duplex, and dynamic in the way the so-called protocol, actually protocol would be the same, it's just how fast it is, right? And having different synchronizations between 2 of those, and this is not static either, because this could change in time, and but also in space. And how do you connect now the brain, which is in this kind of chaotic part, for us at least, with manufacturable digital design? How to connect brain to a machine? How to have this chaos with this structure? How do you link them? That's the question. Because ideally, as for every engineering endeavor, we want to have ultimate peace by interconnected people and with interconnected systems. But as from my side, as always, thank you for listening, thank you for watching, thank you for thinking, and thank you for the ideation. Bye.